Okay, so today I am teaching John McConaughey. This is John. Simplification of distributive loads. And so this picture here is, it's a, thanks John. It's a steel beam, right? This bottom is a beam that's 9 meters long. And all this stuff on it has, it's exhibiting a force on that beam downwards at each specific rate. And so think of it like the top of a building, right? Snow isn't going to fall, like there's going to be piles of snow. In this case scenario, it's perfect. That's a linear line, that's a linear line. Oh geez. But it's not just one spot where it's producing force, it's distributive. And so what we're going to do is we're going to simplify this whole thing. I redrew this beam over here. We're going to simplify that to one arrow. It could be there, it could be there, it could be here. I don't know where it's at. But we're gonna simplify it to one force in one spot at a specific distance from point O. And so what we have to do is find simpler shapes from this big one. So I'm going to rewrite 3 different shapes here right now. Okay, so what I did here was I took off this triangle up here, redrew it right here, took off this triangle right here, redrew it right here, and then I took this rectangle that was left over and drew it right here. And so these are some equations that we're going to use to find both the distance from point O that the load will be on and the force of that load. And so think of it like if I sat here and I tried to find the perfect spot so that this pen balances on my finger, right? Since it's a pretty symmetrical shape, it's fairly close to the middle. If this was a perfect rectangle, then it would be in the exact middle, for example. But for a triangle, it's 1/3 from the base, it's 1/3 of the base from the tall part. And for a rectangle, it's halfway down. And so, for our triangle, for the distance, we're gonna take 1/3 of our base, which is 6, right? So the distance is 2 meters from this edge. So it's about right here, is where the load's gonna be. Same goes for this one. This is a triangle. 1/3 of 3 is 1. So it's going to be about right here. 1 meter from the tall edge. And so for Our rectangle, the distance is just going to be right in the middle of the base. Right here, right in the middle. So now that we know the distance from our point of revolution, we have to find the force. And in order to do that, we have to take, it's just the area. So what's happening here is this shape is, the amount of force being applied is equivalent to the area of the shape. And so, and area is simple, it's just half base times height for a triangle and length times width for a rectangle or a square. And so for this triangle, our force would be half base, which is 6 times 3, which is our height of this triangle, right? Our height of the triangle is going to be 5, that total, minus this part, which is going to be 3. So the force is 4.5. No, 18 divided by 2 is 9. Force is 9. 9 newtons, right there. In this triangle, our force is going to be 1/2 of the base times the height, which is 2, right? 4 minus 2 is that, which is 3. And so these are newtons. So this, for this shape, we're going to take length times width. Now, that's 2, 9 times 2. Force is 18. Okay, so now I'm gonna clean this up and rewrite it over there. Okay, so in order to, what I did here, I rewrote this those 3 forces into a simpler beam. And so, I mean, this is equivalent to that. This distributed load is equivalent to 3 forces right there. And so what we need to do, we're gonna simplify this into 1 force. And so we need to combine those 3 forces into 1, but we don't know the distance from O. And so what we're gonna do, we're gonna find the force, and we're gonna find the moment, right, of that force, and then solve for D. Because remember, moment equals the distance times the force. We're gonna find that, and then solve for D. And so the forces added up, the force over there is just gonna be all these added up. So the sum of those forces is gonna be and our moment of the total thing is going to be the sum of the moments that are sum of the moments of those three forces. And so I mean, we're going to use this same equation. In this case, we know the distance of each force. And so the moment of the green is going to be 2 distance times the force plus the moment of the red, which is the distance times the force plus the moment of the blue, which is the distance times the force. And so that is going to equate to 123 Newton meters. So now that we know the moment and the force, we can find the distance of our total moment. And so to solve for that, D is going to be 123 Newton meters divided by 30 newtons. Right? So distance is going to be 4.1 roughly meters. And so now we have the force and the distance from our spot. So all of that right there is equivalent to a beam. Looks like that, right? That's 4.1 meters from O and has a force of 30 newtons. That's our answer, right there. This picture right here can be simplified into that right there.